Well, today I want to introduce you to a very important technique of integration. We sort of have finished now talking about the general theory of what an integral is and different ways of approaching it in terms of numerical, graphical, or analytical methods. What we want to do now is look at real fundamental tools or techniques that you can use to apply when you actually are asked to do some integration problem. And substitution is a technique for solving integrals. And it's a technique for solving a very special kind of integral, one that's typically very complicated. It's a technique for solving integrals of composite functions. So when we have a composite function, we're asked to take the integral of that composite function. The chain rule is the way we take the derivative of a composite function. Substitution is the way that we will integrate a composite function. They're very much related. In fact, we'll see a little bit today that they are inverses of each other, and it's helpful for us at the moment to maybe stop and review the chain rule before we move on and talk about substitution. One of the things about the chain rule I've noticed lately is that you guys are really still struggling to get that down, seemingly having taken a break from focusing on those particular pieces. We end up struggling a little bit with those in some of the material we've seen lately. So please review the chain rule. You should be reviewing all of the techniques and concepts we've seen so far. But for this example, I want us to take a look at the derivative of 1/6 of 2x plus 1 raised to the third power. I know that I need to use the chain rule here. Recall, I can identify that in this particular problem because I have a function on the inside. I have this 2x plus 1 function on the inside, and that's being acted on by another function that's being acted on by this third degree power here. So I have a function inside of a function. We're taking the derivative of this. I need to apply the chain rule. Recall what the chain rule says is we start by taking the derivative of the outside function. So here it's that function in green, the third power. We multiply that by the derivative of the inner function, that 2x plus 1. So let's take a look at this. Recall that the constant out front here, 1/6, doesn't affect the value of the integral. Now we have to take the outside function and take its derivative. That's going to bring a 3 down and leave us with 2x plus 1 to a power 1 less, or the second power. And we have to multiply this now by the derivative of this inside function. The derivative of 2x plus 1 is simply 2. So this is our answer here. We can simplify this a little bit. All of the constant factors actually cancel each other out. 1/6, the 3, and the 2 multiply together to give a value of 1. So this derivative simply ends up being 2x plus 1 squared, which is a pretty simple derivative when you consider that we started with something a little bit more complicated. What I want us to see today is how we can work this kind of problem backwards. Okay. How do we work this problem backwards? In other words, given 2x plus 1 squared, how do we determine what the integral of that function must be? How do we determine how to get the correct answer in this particular case? This is the tool, this is the power of substitution, is being able to solve a problem like this. So let's go ahead and look at this as an example. This is a good technique to learn by doing. So we'll do several examples for you to be able to see how this technique works. So let's just go ahead and think about the integral of 2x plus 1 squared dx. Now we all know what the answer is here because we just took the derivative, right? And the fundamental theorem of calculus says that derivatives and integrals are basically inverses of one another. So because we know what the answer is here, we could just write that down. But I want to use the technique of substitution to see that we do in fact know what that answer is. The key to substitution is to look at the integral that you're doing and again see those same clues that we saw just a moment ago. That is, see that we have an inside function and that we have an outer function. So we recognize the fact that we are dealing with a problem of composite functions. And so again, I see here a composite function. I have an inner function and I have an outer function. And so in a way, these derivatives are related, so the antiderivatives will also be related. The key to being able to use substitution to solve a problem such as this is to make, as the name of the technique suggests, a substitution. And what we're going to do is we're going to let u equal the inside function. We're going to let u equal the inner function here. Now, the technique of substitution will not always work. In class, we'll go over some examples of things that do not work, that you can't apply the substitution technique to. But in this particular case, we will be able to do this. So in this particular case, my u is going to be the value 2x plus 1. So what this is going to look like now is the integral of u squared dx. And notice what this substitution has done for me. I no longer have a composite function here. I have a very simple thing. I have u squared. Having u squared, I know what the antiderivative of u squared is with respect to u. Right? I know what that is. I know that the integral of u squared du should just be 1/3 of u cubed plus a constant. Doesn't matter what the variable I'm using to express things is. This is a relationship. This is an antiderivative. This is an integral that I know. And that's one of the techniques of substitution. It peels back for us, gets rid of this composite function, and turns the integral into something that we already know. Turns it into something that we can evaluate. Now, there is one problem here that we have to work with, and this is typically the problem that will keep you from being able to do substitution at times. The problem here is that while my integral is of u squared, my differential is still expressed in terms of x. I still have dx here. What I really need, as we can see in this problem, is I really need to have these two things agree. I need to have integral of u squared du. And I don't have that. I have the integral of u squared dx. So we have to do one more step, and that is we have to figure out how to express dx in terms of u. So we need to figure out what the relationship there is between dx and u. So the next thing we want to do is we want to write dx in terms of du. How are these things related? This is what we need to know now to be able to connect up things and deal with a simpler integral. Luckily, we can do this because we have a connection between u and x, and that connection between u and x gives us a connection between du and dx. Recall that we had made this substitution earlier. U is just equal to that inner function, 2x plus 1. If I take the derivative of this expression, if I take du dx, what do I get? Well, the right-hand side, if I take the derivative of 2x plus 1, I simply get a 2. The derivative of 2x plus 1 is 2. And now we can rewrite this expression to say that du is equal to 2 times dx. And now we have a relationship, right? Now we have a relationship where we have written dx in terms of du. There's a connection there, and we can use that to simplify our integral one step further. In fact, what we would like to do is we would like to write this as dx is equal to 1/2 of du. So now our integral becomes much simpler to work with. We actually can come up with our answer right away because we had the integral of u squared dx. We can change that into the integral of u squared times 1/2 of du. Recall that the 1/2 du is simply substituting in here for the differential dx. And a constant, we can pull that out. So this becomes 1/2 of the integral of u squared du. And this is the integral we already know how to do. Right? This is a simple, straightforward integral of a polynomial. So with this 1/2 out in front, we end up with 1/3 of u cubed plus a constant. That is the integral that we're looking at here. The last step we have to do is to simplify and to substitute back in. Recall that u was equal to 2x plus 1, and therefore our integral, if we substitute back in, our integral here will equal 1/2 of 2x plus 1 cubed times 1/3 plus a constant. Or if we simplify this out, we find that the integral of 2x plus 1 squared dx is equal to 1/6 of 2x plus 1 cubed plus a constant. And so here this verifies the formula that we actually came up with, the relationship we found by doing the chain rule. And again, another reinforcement that forwards and backwards, derivatives and integrals undo one another up to a constant. Okay, up to a constant. And what we find here is we have exactly the same value. We were able to do this integral, something that did not look like a polynomial. So this is a very powerful technique. We were able to take an integral of something that was a composite function. Let's look at another example.